And so, yeah, so we're going to be talking about the math of spectroscopy today. So there really, I don't know that there's a lot of notes. There may be some things that there's some blanks in there, but I really want you to just try to really just focus on absorbing the material, thinking about it. Okay, it's not a. We're going to go. I would say it may feel like we're going fast, but I'm going to just try to walk you through a spectrum all the way down to the wave function and back. Okay. So a lot of times when we're teaching quantum mechanics, we start with the wave function, but that's completely intangible. I mean, you can think of a wave, you can think of a string, that oscillates back and forth, or like a guitar string or violin string or something, and you can picture in your mind this idea of a wave, but how is that related to nature? And how would we know if that was the way nature is? Well, it's through spectroscopy. So let's start with the tangible stuff, the data, and go deeper into where we see the wave function. This is all about Schrodinger's cat and so on in quantum mechanics. This is kind of funny. Babylon B, Schrodinger's neighbor. He really just wants to know where his cat is. It's kind of funny. Yeah. So Schrodinger's cat is related to this idea of wave functions and so on, but it's pretty funny. So what we're going to do is we're going to manage today the messy math of quantum mechanics and spectroscopy. So this is chapter 2 in that book. So start with some critical vocabulary, though. There's a difference between energy levels and spectral lines. And what I want you to really cement in your head right here at the beginning of class is that a line in a spectrum, so if we have a spectrum, we have these peaks, and those are spectral lines. So like this emission line might be here, right? And this one might be here, and this one might be here. The reason we call them lines is because back in the old days they had a narrow slit and a photographic plate, and so when they developed the photographic plate, they saw lines where the emission took place. Okay, so it was in a photographic plate they saw these lines, which was really the image of the slit on the spectral photographic plate. Now, lines are always differences between levels. You see the levels, the energy levels. So what we really want to be comfortable with in this course is an energy level diagram. Because if you can draw the energy level diagram, then you can understand the spectral lines and vice versa. Okay. So these energies are quantized. Light is emitted as an electron or nucleus or atom or molecule drops from a higher energy level to a lower energy level. So differences in levels gives us spectral lines. And those can be emission if it's dropping down, or if it's going up, it's absorption. Or if it's bouncing off and it changes energy, it might be scattering. So we'll learn about Raman scattering and Rayleigh scattering too. So light is absorbed, causing an electron, nucleus, atom, etc. to jump up to a higher energy level. So this is the very basics of all spectroscopic methods. If you can draw the energy level diagram, you can understand the technique, at least at the science level. The lowest level in a system is going to be called the ground state. Okay, so this is another thing that you need to keep in mind. Oh, my eraser's not working. See if I can. Anyway, ignore the red lines. Long wavelength, low frequency, low energy difference is associated with a short arrow. You see this short arrow? This is the shortest arrow in the diagram, and that's going to give us a long wavelength. It's going to give us a low frequency and a low energy difference. So those are all related to each other. Long and low. Long wavelengths, low energy difference. Okay. If you have a long arrow, okay, not a long wavelength, but a long arrow, that's a short wavelength, a high frequency, and a high energy difference. So if we go and collect a spectrum, let's say we look at the spectrum of a hot object, like if we run current through a wire, like a tungsten wire, it'll be very bright. And it'll also burn out if it's in oxygen. So Thomas Edison put it in a glass globe and sucked the air out, put it in a vacuum, and he created a light bulb. But the light bulb is really just a hot wire, okay? And the spectrum that it gives off is a function of temperature, not the material. And that's kind of a weird thing. Physics couldn't understand that, really. And it didn't matter if it was tungsten or copper or whatever, the wavelengths of light that came out were just a function of its temperature. So that's interesting. Then we end up with the tungsten halogen bulb. What is the halogen part? Well, we're not really getting emission from the halogen. What we're doing is we're letting the wire heat up more without subliming the metal off. And so the halogen keeps the metal from getting thinner and thinner and burning out quickly. So they put in chlorine or typically chlorine, and that helps the tungsten last longer, but it also results in a higher temperature. So tungsten halogen lamp is just even brighter white and gives off more white light because it's hotter. The downside of that is that there's now a gas in there, not a vacuum. And so collisional energy transfer from the hot filament to the outer glass makes the glass too hot and the glass melts. So they make them out of quartz. So a tungsten halogen lamp gets super hot and it has to have a quartz jacket. And if you touch it with your oily hands, you can create a zone of the quartz that's going to cool off because of the oils, and it'll crack and break. And so anytime you're replacing a tungsten halogen lamp, you need to use gloves because the lifetime of the bulb will be decreased dramatically if you use your hands on something that's going to get that hot. So this is the blackbody radiation curve. And we talked last time about Rayleigh-Jean's law and Planck distribution and so on. But this blackbody radiation profile is well known, and it's the basis of what we call color temperature. So you can go to Home Depot and you can buy different light bulbs, and they'll list a color temperature on there. My wife is very particular. She does not like the yellow bulbs, like the warm ones that are 4,000, 3,000 or 4,000. She doesn't like the 7,000 ones. So she doesn't like those. She likes a 5,500. That's just the light that she likes. And so whenever we buy light bulbs and stuff, if we buy one that's a soft white, which is the 4,000 Kelvin, and again, it's related to these temperatures over here. You can see that 3,000 is way too red. There's almost no blue, right? It's giving off this amount of light. 4,000 is a little better. You get some yellow, some green. 5,000 is a lot of visible light. You know, it's getting all of the wavelengths here. And so it's very good. We get to 7,000, 8,000, 10,000, then it starts to look blue. Anybody work at TRIS? Anybody? We have an environmental sampling lab here on campus. They have an inductively coupled plasma. And it runs at 10,000 Kelvin. And the light coming off of that, a lot of it is just argon. It's in the emission spectrum of argon. But it also can emit blue because it's 10,000 Kelvin. So it would look like a blue flame if it was a black body. Now that's the Planck distribution curve. And it matches experiment. But it's pretty complicated. Let's try to model that curve using a particle in a box. So visualizing the blackbody process is pretty difficult, but visualizing an electron on a wire is easy. So if we have a wire here, and we have an electron that's somewhere on that wire, and we model it using the wave functions where we have, say a wave function for that electron on the wire, we can take that idea of this wave function and get this curve right there, which matches the black body curve pretty closely. Okay, it's not exact because we're using Gaussian line shapes and not logarithmic line shapes, but still pretty darn close. Now this is what physical chemists do. There's actually a joke. You could look it up. It's got its own Wikipedia page. It says, let's begin with a spherical cow. Okay, because a chemist, a physical chemist in particular, when asked to model a process, always wants to go to the simplest model first. And so the joke is a farmer asked a physical chemist to model his pasture and his pens and everything like that. And so he comes in and he says, well, let's begin with a spherical cow. Right? Because that's a simple model. How many balls can we put in this field, and and in this pin, and so on. And so, a cow is not even close to spherical, right? And a particle in a box is not even close to this macroscopic object or a tungsten filament inside a light bulb with halogen gas and all of that. But it's a great first model, and we can get that close with our simple model. Okay. So this idea of beginning with a spherical cow is a common joke. But the point is, if you can simulate it, you can understand it. So let's start with these transitions that we're going to be able to simulate. So here, this is the first homework that's due tonight. So we have some questions on these particular transitions. And so you're going to be tested on just being able to specify which of these transitions is associated with which phenomena. And I really want you to be able to draw these. If I find you on campus, stop. Here, come to this dusty window and draw me a Rayleigh scattering energy level diagram. So I want you to be that ready to do it because it's that important. So this is absorption. So light comes in, hits the system, and excites it. So the light has disappeared. It has been absorbed. And now the system's at a higher energy. Now could be infrared, it could be UV vis, it could be any technique, it could be even NMR. Okay, so light comes in and is absorbed. Okay, and so the system finds itself at N prime, which is the second state, and it's got higher energy. The opposite could happen. Let me go to the opposite of that one: spontaneous emission. So you've got an excited molecule or atom or ion or whatever, and it drops down simultaneously spitting out a photon. So the energy is lost in terms of the photon, and it finds itself in a lower state. Now this happens instantaneously, and that's what Schrodinger hated. He hated this quantum jumping. What caused it to fall down, we don't know. Even to today, we don't know. There's no way to predict. If I've got an atom and I'm staring at it, there's no way to predict when it will drop. Now, on average, I could get a statistical prediction, a probability. And those hold pretty well. But for individuals, you can't know. Just like flipping a coin. If I flip 1,000 times, the numbers of heads and tails are going to be close to 50-50. But each individual flip, I have no idea. I flip that coin, I have no idea if it's going to be heads or tails. So we can think in terms of probabilistic, occurrences in terms of time. We know this happens at a sort of a proportionality to 1 over the wavelength cubed. That if you take that energy difference, convert it to wavelength. This is the spontaneous emission lifetime that will stay at the upper state. So we have absorption, and then it's going to stay up there for a time proportional to 1 over lambda cubed, and then it's going to drop down. So that's our average lifetime of the upper state is related to 1 over the wavelength cubed. But let's talk about stimulated emission. This is the basis of all laser systems. So laser do y'all know how to do that? What's the LASER? Laser, it stands for something. Light. Laser, light. Nope, it's not absorption, but that's a good guess. Light. So we're stuck at the A. What about S? Stimulated, yeah. Yes. That's what we're talking about. Yeah, stimulated emission in the R. Radiation, yeah. So the A, what is the A? Amplification. You looked it up. Look at you. Sneaky. You put it down first. But look what's happening. So a photon comes in, and the molecule has to already be excited, and then look what comes out. 2 photons. That's amplification. Okay. So the light that hits it has to match this energy difference, and if it does match this energy difference, it will stimulate the emission, and 2 photons come out, and they're in phase with each other. So we got 1 coming in, it stimulates the emission, and 2 are coming out. So we've doubled the amount of light. And so the whole trick of a laser is getting molecules in the excited state, population inversion, more molecules in the excited state than in the lower state, and then a photon light comes through and stimulates the emission of all of those excited atoms, ions, or molecules, and we get lots of amplification of light. So that's the stimulated emission. the probability of this occurring is the same as the probability of absorption. So you need more than 50% of the molecules in the excited state, otherwise you'll just get absorption. So if you have all the molecules in the ground state, you can't have any stimulated emission because there are no molecules in the excited state. But the probability of absorbing is the same probability as stimulating a drop down. So if you can get more than 50% of the molecules in the excited state and you send a photon at the right, what we would call the absorption line, but you send it in, it's going to create emission and it's going to amplify them. So that's the basis of the laser. These are all of the three. There's absorption, emission, spontaneous, and stimulated. Then we get to scattering. So we have elastic scattering, which is named after Lord Rayleigh. Okay, and I draw those little squiggly lines just to show that they're sort of off scale. I've sort of changed the scale there. So these would be very, very long lines. Typically, these energy levels might be, say, in the infrared or vibrational region, and this would be visible light. So it's coming in and bouncing off of the molecule. Now, it's how do you know it bounced off the molecule? Well, it changed direction. So light's coming in, it interacts with the substance. Let's say it's visible light. So the substance's electron cloud oscillates with the light for 10 to the minus 15 seconds, almost nothing. Very, very short period of time. And then it stops oscillating, which means the light is now emitted. So it's like an instantaneous absorption and emission. So you see the up and down arrow. Now it doesn't hit an energy level. If there was an energy level up there where the dashed line is, then it would absorb. So it's oscillating, but it's not absorbing. So the light is interacting with the electron cloud, but it's not being absorbed because there's no energy level there. And we know scattering happened because the light changed direction. If light doesn't change direction, that's the phenomenon of reducing the speed of light in a medium. So that's the refractive index. So light's going into the material and it slows down because it's a lot of instantaneous oscillations with the light and re-emissions, but it's on the same path. And so we don't call it scattering. We just say that light slows down when it enters a medium. So the speed of light in a vacuum is the fastest it can be. As soon as it enters air or glass or water, it slows down dramatically because of the electrons that are in that substance, and it oscillates with that light and slows it down. You could think of that as a bunch of very quick absorption and emissions that take place. Now, if they emit at a different angle, that's scattering. And that's Rayleigh scattering. If there's no change in energy, look at the wavelengths. They're the same. You see up at the top and down here, wavelengths are the same. The arrows are the same. What if the arrows are different? Then that's inelastic scattering or Raman scattering. So in this case, we have a long arrow. The light comes in, oscillates with the electron cloud. But then when the molecule or atom stops oscillating, if it ends up in a higher state of energy, then some of the light energy is missing. So it'll come out at a long wavelength, a red shifted photon. So we'll say Stokes Raman is red shifted. Longer wavelength. Okay. This has a shorter arrow. You can see that too. So the photon that went in was a long arrow, and the one that came out was a short arrow. So that gives us a red shift of the light. So that's Stokes Raman. If we have molecules that are already excited, so we have molecules that are already excited, then you can get anti-Stokes. So that's a blue shift. So you see this longer arrow was the down arrow, the longer one. And so that photon that comes out has got a shorter wavelength. It's shifted towards the blue side of the spectrum. So these are the 6 spectral transitions that we'll talk about in this course. They cover all of spectroscopy. These can be in the X-ray region, dealing with like core electrons, 2s, 2p, and all of that. This could be in the infrared, looking at vibrational energy levels. This covers all of the different spectroscopies. Okay. And your homework tonight is just identifying which one of these, and then it has some stuff from the history lecture. So in the chapter, you can. Yeah. Okay, so now let's look at this. Let's look at a spectrum. So we started here. We're going to simulate this Planck distribution using a 1D particle in a box model. So let's look at that. So if we were to write an equation for the absorption profile, here's what it would look like. So it's I tried to make it as simple as possible. So what do we want in an absorption spectrum? If we're going to put our sample in and we want to get a spectrum out, we want big peaks. We want a lot of signal. And so I said the absorption needs to be big. So BIG. You see that? We want it to be big. And that just happened to work out nicely that B is Boltzmann, I is an integral, and G is a Gaussian line shape. Okay. So we have all of these things labeled. So we have this absorption spectrum. If we were to write the equation for an absorption spectrum, it's going to be a function of temperature. There's a temperature piece. It's going to have something related to the instrument. Spectral resolution is in there. And then it's going to be plotted versus wavelength. Now we could also do like wave number and other things, but for this particular thing, let's just plot it versus wavelength. Okay. So those are the factors that affect our absorption intensities. So the thermal population piece is the Boltzmann piece, and we're gonna expand each of these and look at them individually. But I just want to describe to you what BIG stands for. But don't take a picture yet. There's going to be all kinds of more stuff on there. No, that's okay. You'll have 50 pictures in there. So this is the Boltzmann piece. It has the probability of being in the initial energy level. So the initial level could be an emission, it could be the excited level if it's emission. Or the initial level could be the ground state or lower state if it's absorption. So that's why I'm saying initial, not lower, right? If it's absorption, it's the lower level, but it could be emission, so it could be the upper level. So we want to talk about initial and final, not lower and higher, okay? So the Boltzmann, if there's no molecules in the upper state and you want to do emission, you're going to have zero signal. Your signal's not going to be big, right? Because the Boltzmann piece is very low, you know, at certain temperatures for the excited states. Okay, so if we want to get more molecules in the excited state, raise the temperature, and then you get more molecules in the excited state, and then you can do emission spectroscopy. Okay, this last piece, or the middle piece, I, is the integral. We're going to spend a lot of time on the integrals today. We're not going to do them, but we're going to show where they show up. Okay, and then G is the Gaussian line shape function. We'll have a whole lecture on different line shape functions, but we're just for now going to use a Gaussian, the normal distribution. And in it has a certain width, right? We call that standard deviation for a normal distribution, but in our application, it's the uncertainty of the spectrometer. So it's the spectral resolution, okay? So that's the delta lambda. And then we have the individual peak positions, right? If I have a difference between energy levels, that difference gives me a spectral line, and that line shows up at a wavelength. So that's the spectral line right there, the transition wavelength. Now, if we just have one energy difference, we're going to have one spectral line, but nature has lots of energy differences. So we're going to have lots of spectral lines. And then if we plot that versus wavelength for each one of those spectral transitions, and then we sum all of them up. So if we have 50 spectral transitions, the overall spectrum is going to be a sum of all of those individual peaks. It makes sense, right? We have a thermal piece. If I want to simplify my spectrum, I cool it way down so that there are no molecules in the excited states, and I just have one little ground state situation, and it can absorb light, and that's all. Okay, so that's at really low temperatures. And then this integral piece, that has the wave functions in it. So we haven't gotten to wave functions yet, but we want to know what's the intensity. I could also be intensity, okay, but our intensities are proportional to integrals of the wave functions. So here it is in the picture form. So this A equals big is this curve right here. You see it's labeled A. And that's our black body radiation curve that we're modeling with our particle in 1D box, okay? Here's the Boltzmann piece. This is the difference. This first peak is the ground state to first excited state. So it has the highest probability of being populated because it's the ground state. Okay. And so that's the Boltzmann piece. It's up here. But then as I get to excited states, this is the first excited state going to the second excited state. So it's a little less probable to be in the first excited state. But I'm at a really hot temperature. I don't have it on here, but it's 500,000 Kelvin. Yeah, here we are, 500,000 Kelvin for an electron on my little wire. Okay. As I go higher, this is the third excited state going to the fourth, or the fourth going to the fifth, or the fifth to the sixth. You see, it's way less probable to be in the sixth excited state. Even though I'm at 500,000 Kelvin, it's still not as probable as being in the ground state. So that Boltzmann factor goes to 0 as I go up in excited states. And that's why the hot body, the black body curve goes up, but then it comes back down to 0 because it's emission of a hot object, and a hot object's not at an infinite temperature. It's at 4,000 Kelvin or 5,000 Kelvin. But the super excited states aren't excited, even at 5,000 Kelvin. And so emission eventually goes to 0 at low wavelength, not to infinity. If we could get that substance to an infinite temperature, then maybe the emission would go to infinity, but we can't achieve that. No substance can survive that. Yeah. So the black body radiation curve, this is how Planck solved it. He said, what if we have little oscillators and the probability of exciting those oscillators drops off because of the Boltzmann distribution? He stole Boltzmann's math and accidentally discovered quantum mechanics. So it's pretty cool, yeah. So that's why I say Boltzmann's the father of quantum mechanics. Okay, so that's the Boltzmann piece. The I piece is related to the wave function. This is the ground state to the first excited state. Those two wave functions are here in this intensity piece, or this integral piece. And then there's wave functions associated with this transition and that transition. And then, so that's the wavelength of transition from 1 to 2. This one's 2 to 3, 3 to 4, etc. And then we will dig deeper into those two parts. But then we have this Gaussian line shape. So this is the sort of stick that's related to the intensity of this 1 to 2 transition, but our spectrometer is not perfect. It's not going to measure 0 light, 0 light, 0 light, and then all of this light, and then go back to 0. It's going to have some resolution to it. And so this shape with the uncertainty in wavelength is going to give us this Gaussian curve. And we put one of those on every one of the transitions. And then we sum them together. So even though these peaks are really small, look at all of the signal we get in the spectrometer from every one of those small transitions. And then the overall thing is summed. You see the summation sign. So all of these small peaks are added together, and it gives us that really large peak. So what looks like 3 peaks, right? A peak here clearly, a peak here clearly, and a shoulder. So it looks like 3 peaks in our spectrum. So if you were to go to your UV spectrometer, put this system in the cuvette, stick it in there, collect a spectrum, you see this shape here, you say, oh, I've got 3 peaks. But there's really 36 transitions here. And y'all are going to build the spreadsheet that produces this graph. That's one of the projects. So the numerical theory project is this. You're going to build this spreadsheet that does this. So you'll understand all of these equations. Okay, so let's talk about these integrals. There's a vocabulary piece called Dirac notation. This is a philosophical syllogism. Humans are lazy. Dirac is a human, therefore Dirac is lazy. Right? And so he got tired of writing the integral with respect to the x. And he just started using these angle brackets here. Okay. So those mean the same thing. The integral over all space, so this piece right here and this piece right here is simplified using Dirac notation. So I could not be lazy and write out all my integrals, but then you wouldn't know about Dirac notation. And so I think you need to know about Dirac notation because you go to a physics class or something like that and you're going to see all these little bras and kets. They also call this bracket notation. And so this is the bra and this is the ket. Bracket notation. Strange, I know. So that's and typically we do this in 3 dimensions, but in our particular problem, we have only a wire that the electron is on. So we just have 1 dimension, and that makes the math much easier. So let's look at that integral piece, the I in big. For absorption and I'll say stimulated emission. Absorption and stimulated emission, we have the same intensity piece. And it's the integral over all space of the wave function for the for the final state and the wave function for the initial state. And then this X piece. This X is simulating light, and we'll talk about that in a sec. But here are the wave functions. Now we don't know what the wave functions are, but this is at least where they show up. They show up in that intensity piece. Because we have the ground state behaving like a wave, and then we have light coming in behaving like a wave, and then we have the upper state behaving like a wave. So we have 3 waves. How do these waves match? Well, we multiply them by each other. So if one wave is up while the other wave is down, and we multiply them by each other, I've got positive numbers times negative numbers. Let's see, yeah, positive numbers times negative numbers, and then I'm going to integrate. Let's do it this way. We have a wave function that has a positive piece or negative, it doesn't matter, and we have a wave function that has a 0 piece right there. And I'm multiplying a positive piece times 0. Okay, it's canceling out. So when we multiply these wave functions by each other, we're looking to see if they cancel out or if they get stronger. Okay. And then how do we know? We've still got everything, multiplied by each other. We sum them together. That's the integration part. So we sum these interactions. Maybe we have some strong cancellation. We got a non-zero piece times a 0 piece. So that part's canceled out. But over here, we've got a positive piece and a negative piece, and it's not 0. It's negative because we got a negative. And over here we have some positive pieces times some positive pieces. It's non-zero. Maybe the positive and negative pieces cancel each other out when we sum them. And so that integral will be 0. So the probability of that transition will be very low. But if we have, after multiplying these wave functions together and we integrate over all space, we have something that's non-zero. Maybe it's negative. We square it, and that intensity is proportional to the square. So all the negative pieces become positive, and we end up with either a strong intensity, a weak intensity, or 0 intensity. But it's a way to take into account the interaction of all 3 waves. What are the 3 waves? The lower state, or no, I should say the initial state, light, and the final state. We could do the same thing with scattering. And here it's using x squared. We'll talk about why this is x. This is the actual dimension x in our system. Okay, and we'll talk about why that is. That light's coming in as a dipole. So if you look at light polarized along the x-axis, it has a positive and negative piece, and it's going to interact with those wave functions with its electric dipole moment. And this is the electric dipole approximation. The one simple sort of classical way to think about scattering is there's 2 photons of light. There's one that comes in and one that goes out. And so we have 2 x's. So that's why it's x squared. That's sort of a simple explanation as to why there's an x squared there for scattering. Let's look at the Boltzmann piece. What we want to do is calculate the probability of being in energy level N. So this is the one we're curious about. And this E1 is the ground state. So this is the degeneracy of level N. So it's a counting experiment. We're looking at probabilities. So that means we're counting things. And you're familiar with degeneracy already. So like think of your atomic orbitals. Like the 1s orbital, 2s. Well, let's get to the 2p. Notice there's 3 equal energy levels. And so that would be the degeneracy of 3. So that's what the G term means in the Boltzmann distribution. When we get to the d orbitals, there's 5 equal energy levels, and so the G term would be 5. So that's what this G of n means. It's again making sure we have correct statistics. This is the energy level we're interested in. It could be the initial or the final, it doesn't matter, but it's the initial level because we're about to do a spectroscopic experiment. And then this is the ground state. So what we're doing is we're saying how high is the energy level N above the ground state. So we're setting the ground state at 0 essentially. And we're seeing how much temperature does it take to populate that energy level. So here's Boltzmann's constant. And then here's the temperature of the system. And this is the thermal population. So that's what's given by the Boltzmann distribution. If something matches the Boltzmann distribution, by definition, it's at thermal equilibrium. Okay, so this is how we define thermal equilibrium. It's at the Boltzmann distribution. Okay, and now let's calculate those energy levels. So the Boltzmann distribution requires energy levels of the system, but where do those come from? They come from the Schrodinger equation. So this is a wave function of level n. Also the Hamiltonian total energy operator. We're going to expand that in a second. And this is the wave function of level n. So this is the Hamiltonian operator operating on that wave function and then left multiplied by that same wave function. So both of these are n's, no n primes here. Okay. And this sandwich type structure of function, operator, function is called an eigenvalue equation. Now we could go deep in the rabbit hole on that one. But this is the Hamiltonian operator. It's the total energy operator. And this is the important piece here. It has a second derivative operator. So that's why it's not just numbers multiplied by numbers. This one actually does something to the wave function. So it takes the second derivative of the wave function. Okay. It also multiplies it by Planck's constant over 2 pi squared, and it has the mass of the particle. So this is where you also have the potential energy function, which luckily for our system is 0 across the whole box. So we just get rid of V. It has the second derivative operator, Planck's constant, which is given there in like 8 significant figures. And the H bar, once again, humans are lazy and physicists are human. So this little bar here indicates that it's H over 2 pi. Like who would know that? You just start putting bar on there. So they got tired of writing over 2 pi. So, and then M for our system is the mass of the electron. Now these wave functions have certain criteria. They have to be compatible with the second derivative operator. So this goes back to calculus a little bit. If I take the second derivative of x cubed, so what's the first derivative of x cubed? We bring the 3 down and drop the exponent. So it should be 3x squared. And then I take the derivative again. So 2 comes down, 2 times 3 is 6. And then the 2 goes down to 1. It should be 6x. Okay. But notice I started with x cubed and now I have x. So a polynomial like x cubed and so on would not be compatible with this eigenfunction. This second derivative needs to produce the original function. Okay. So then that means we have to use oscillatory functions like sines and cosines. Because what if I take the the first derivative of sine x, the derivative of sine x? It's a little review. Okay, goes way back. Derivative of sine is, well, the derivative is what? It's slope, right? So can you draw sine in your imagination? Here's 0. Sine starts at 0 and goes up, curves down. Okay. What's the slope as it passes 0? Rise over run. So it goes up a unit and over a unit. should be 1. So the slope of sine at 0 is 1. Do you know an oscillatory function that at 0 has the value of 1? Cosine. So the slope of sine is cosine. So the derivative of sine is cosine. Okay, yes. Now, let's take the second derivative. We've got cosine. Now, we're taking the derivative of cosine. The slope at 0 is 0, right? It's flat, okay? And it starts to go down, okay? It's the opposite of what sine does. Sine goes up right after it leaves 0. Cosine, the derivative of sine, goes down right after it leaves 0. It's minus sine. So the second derivative of sine is negative sine. So we get sine back. So sine and cosine, both of them actually, are oscillatory functions that are compatible with the second derivative operator in the Hamiltonian. So that means our wave function needs to be either sine or cosine. So that's where this wave function, we start to get a hint as to what our wave function would be. And it's going to be a sine function. And here it is. Here's our particle in a 1D box wave function. So it's sine of the quantum number and pi and x and so on. And we'll build this one in the next lecture, but we're just giving it to you right now. This first piece is the normalization constant to make sure that when I square the wave function and integrate over all space, I get 1. So that forces that to happen. Here's our quantum number n. It has this n pi over 2 piece. This is a phase shift to make sure it's centered on 0. Okay. Each level has a wave function. The function has a spatial domain. So our little wire is the x-axis that our electron is sitting on. It has this normalization constant. We'll talk about that in a future lecture. It has a compatible function that's compatible with the eigenvalue operator, second derivative. The length of the box is L. Okay, so that's the length of the wire. We call it a box for some reason. That the electron can't leave. Okay. And then it has this phase shift to make sure that the wave function is centered on 0. That's a unique thing to the way I teach it. If you go to any physical chemistry textbook and look up the particle in a box wave function, it won't have this phase shift on it. It will just be n pi x over L. Now, why is that important? Well, I like symmetry too. And so I want my wave functions to be symmetric on around 0. I don't want them to start at 0 and go one way. I want to be able to look at the symmetry of this function as it relates to positive and negative direction from 0. So here they are, and you can see that it's centered on 0. So the center of the wave function is here at 0. And notice how the left and right for this ground state look the same. So that means it's an even function. We'll get to that later, but look how this, they're equal and opposite in n equals 2. And so by centering them on 0, I can say things mathematically about their symmetry. I can say that they're odd functions or even functions, and that becomes very handy in the future when we start talking about symmetry. Now it's confined to this box, this wire, by setting the potential energy to be 0 here in the middle, and then at the end of the box going up to infinity. So it can't leave the box. To leave the box, it would have to have infinite energy, so it can't leave. This is a mathematical way to confine it. So those set up the boundary conditions, the walls of our box. Some other terms here are given, the node and lobe. So where it crosses 0 is a node. Where it's oscillating, where you can tell it's oscillating, those are lobes. Okay, and so at some time later it'll look like this. So you can picture that oscillating up and down. Okay, what happens when it passes through 0? If I were to take a snapshot, this is sort of a philosophical question, does it cease to exist?
Now it's shifted up to the left.
It's what?
But cease to exist before shifting the function to the left. So you have a
Well, it's fixed between these two walls, yeah. But like it's oscillating. Let's just take the bottom one. It's going up above and it's going down below. But what happens when it's right at zero? It seems like there's no function anymore. What it does is when it's being considered in terms of time, it becomes an imaginary function and it oscillates in and out of the imaginary plane. And so when we see in the real plane it going to zero, it's actually moving towards the like plus I, and then it goes to negative real, and then negative I, and then positive real. So it's doing this really, if you want to think about the imaginary planes. So if you're not cool with imaginary numbers, that's fine. But I just sometimes people say, well, what happens when it's right at zero? Then we get to transition equations, the differences in these energy levels. So we take the final state and minus the initial state, and we get this delta E. And these are the line energies, which are the difference between the levels. So we can convert that to frequency by dividing by Planck's constant. So that would be the transition frequency. Or we could take into account the speed of light and calculate the transition wavelength. So this is the transition wavelength that we have in all of our equations. This is related to the horizontal axis in the spectrum. This is where the peaks show up. We use Schrodinger equation to give us the energy levels. We take the differences, calculate wavelengths, and that tells us on the horizontal axis why this peak is here and not there. It's related to the wave function. The A equals big, that's the vertical axis of the spectrum. That's how all of the transitions add together and give us an intensity. Okay, that's the speed of light. So putting it all together, we have that wave function. That wave function is used to give us the energies using Schrodinger's equation. Okay. Once we have the energies, we can calculate the changes in those energies with the different transitions and come up with the transition wavelengths that show up here. So this transition equation tells us about the horizontal axis, where all the transitions occur. And then we calculate the Boltzmann distribution based on these energies. We have all those energies, we put them together with temperature, take the exponent. If there's degeneracy, which in our system there isn't, then we calculate the Boltzmann populations of those energy levels. We have to take the integral of the final and initial wave functions as they interact with light. And that gives us the intensity of the transition. Okay. We square it because it might be negative. Okay. And we get the intensity factor. That's this I piece. And then we put it in a real spectrometer that has a spectral resolution, and that's the Gaussian piece that has this delta L, delta lambda here, because no spectrometer is perfect. Okay. Then we sum all of those individual peaks together, and we get the overall spectrum. So hopefully you can see now that the wave function is present in the energy levels, which gives us the transitions about the horizontal axis where the peaks show up. And the wave function is also present in the intensity piece, determining how they interact with light. So we cannot understand spectroscopy without quantum mechanics and waves. This is the solution to all of it, is understanding the wave function. If you understand the wave function, you can model any kind of spectrum that you want. Now, you don't always have to go to the wave function. This is a really deep theory. Let's say you're in a forensic situation or you're an applied chemist. All you really need is the energy level diagram. So if you can draw the energy level diagram, what we started this class with, the scattering and all of that, then you can understand the spectroscopic technique. But know that those energy levels are where they are because of the wave functions. You won't ever have to really go do that, but I want to teach you the theory so that you can understand why those energy levels are where they are. Okay. Now, what is this Kahoot? We're out of time, so we can't do it in class. But if you go to Kahoot, Google it, okay, and search for chem_prof, you can find a Kahoot that will test you on all this material we covered today. So it'll be a good review. Yes. This, which one? Okay. This one? Yeah. Okay, great.